It's a real pleasure to be here to talk to you and to see young faces arriving in the lectures. And it's a real pleasure to be here. This is 5 years more maybe that we are collaborating. And in particular, we collaborate in waves, but this year we are collaborating more precisely on waves in stratified flows. But the application, what we want to do is not directly, in fact, astrophysics or geophysics. That will be another part of physics that we would like to develop. So here, as you said, my colleagues and I, we are in a team, we are merged in a team called Rotating Flows and Geophysics, because a lot of applications in geophysics and astrophysics have to deal with waves in these two kinds of flows. Okay? So I try to explain to you why we have these waves. Certainly you must know that these waves exist already, and we try to develop very simple concepts. And after I need this part, after I would like to show to you 2 experiments. One experiment was done 10 years ago, okay, with my colleague Michael Levars. And in fact we did the experiment because we read the first paper about this possibility of instabilities. But in fact, we didn't really understood deeply what we were doing in the lab. Okay? And it is only now, 10 years after, that we realize what we were doing, but not only us, or not the community, what happened in different flows, and how you can play with waves, and how you can make these waves to resonate and appear in fluids. Okay? So, and that will be the second experiment that was performed by the last one here, Julio. So Julio just finished his PhD last year. And all these students, of course, have been my students or with other professors here. And now they are professors in universities, okay? Now they are grown up also. And they became professors. So let's start. So the first wave that I would like to introduce to you is called inertial waves. And these waves are, in fact, the natural response to a fluid when you have rotation. So let's consider a bucket of water. You rotate this bucket of water. Imagine you are inside the bucket. If you move a little particle of fluid of water, because of the Coriolis force, okay, this Coriolis force will act on the velocity 2 omega cross v. So that's the central force. And this thing, okay, v is like that, omega will be like that, the force will be like that. So this force will act as to put the particle back to its position. So in fact, the Coriolis force can be seen as a restoring force, exactly as a spring, when you know a spring on a mass, okay, for the gravity field. So if you take the equation of the fluid, and you say, okay, I don't want to deal with viscosity. I suppress viscosity. And this is true when you have big dimensions like planets or atmospheres, or in astrophysics, geophysics, this is usually the case. So you can forget the viscosity. Another term which is much more difficult to deal with is a non-linear term. Okay? It's a v grad v from the Navier-Stokes equations. And this v grad v term, you see that's v and v. So this term can be small, is itself small. Okay? V grad v is smaller than v. So we say, okay, we make a small perturbation in my bucket of water there. The perturbation will be small, so I can neglect also the nonlinear term. So the only term that I have in my equations, in the earlier equation, is du dt, okay, the change in velocity, Coriolis force, 2 omega spin, omega spin is the rotation of the fluid, equal to the minus the gradient of the pressure. Okay, so this is the linearized, because I suppress the nonlinear terms, and this is, that's why it is called Euler equation or non-Navier-Stokes equation. This is in the rotating frame. And in fact, if you play a little bit with this equation, in fact you have to take twice the curl of this equation. And that was done by Poincaré in 1910. You end up with this equation, okay? dt squared over dt squared and here you have the Laplacian of the u, and here you have the 4 omega squared d square u over dz squared. And you see, this is a wave equation, in fact. And this wave equation, you see, is not symmetric in all the variables. The z plays a very particular role. Okay, the z, that is the axis of rotation, plays a particular role. And this equation we know now, and in particular that was studied at the beginning of the 70s, 60s, 70s, that you have waves, solution of this equation, and these waves can be visualized, and that was done, an example here in the book of Greenspan from MIT, okay? That was done in 76. He took a cylinder of water here, and he had an axis, and he has a little disc which is tilted versus the axis. And when you rotate the axis, you rotate the disc, and you see that you push the flow in this strange manner. And what you observe, maybe you can see, so that was 76, you see this pattern of waves, okay, which are the inertial waves. Okay? So these waves are in fact conical waves, okay, and sometimes you see the waves are doing that. Sometimes the fluid will rotate more fast than the ambient. Sometimes it will rotate less fast than the ambient. Okay, so these are the inertial waves, and we can go a little bit further in doing the mathematics of that. So you remember my equation, du dt plus 2 omega v equal gradient of p. I write this equation in the Fourier space. Okay, I put a wave in the system, solution of the system. You finish up with this equation, and you have to add also the no divergence of the flow. Okay, no compressibility. So you have also here du dx plus dv dy plus dw dz equals 0. You play with this equation. This is very simple equations. Okay, linear equations, and you end up to express the frequency omega. Omega is the frequency here, versus the wave number. Gamma is the wave number versus the z-axis. Alpha and beta versus the two horizontal axes. Okay, so this equation can be cast under this form, or here omega square equals 4 omega square, omega being the rotation of the fluid, cosine square theta. Cosine theta is the angle between the wave number k, alpha, beta, gamma, and the axis of rotation. So you see these waves are very strange, no? They give, usually a dispersion relation gives a relation between wave number and frequencies. Here it's a bit strange. It's between wave number and the angle, the frequency and the angle of the wave number. So these waves are very, very strange, okay, compared to light or compared to sound or compared to even surface waves. One other property is that phase and group velocity are orthogonal. Okay? When you oscillate a little cylinder in a rotating fluid, this is what happened, and that was demonstrated by my colleague, our colleague, Frédéric Moisy in Paris, and you can try to find this video on his web page. In fact. So this is a PIV measurement in a horizontal plane above or under. Okay, there is a pattern of the same waves under. That crosses this horizontal plane. So you see in red it is when it is a cyclonic rotation, and in blue when it is minus cyclonic, as in anticyclonic. So these are these waves, the inertial waves. Okay? And if you plot, for instance, omega divided by capital omega as a function of gamma, the vertical wave number, you have this kind of dispersion relations. Okay, you change the different alpha, different beta, and the different gamma, and you have these families of curves. What else? You see that these waves are dispersive. Okay, the phase velocity is the tangent of these curves here is not the same everywhere. Okay, so their velocity is not the same when you change the frequency and the wave number. Okay, this is the first ingredient in my demonstration. A particular case, this is for Benjamin, okay? These two slides. So this particular case is what maybe you heard about these Rossby waves in the atmosphere, and you can understand Rossby waves very easily from the inertial waves that we saw before. So to do that, you say, I will consider that the atmosphere of the planet is so flat, okay, that I have only 2D motion. Okay? So you make this approximation. D over dz equals 0, W equals 0. Okay? You rewrite the equation that we saw before, so you have only 2 equations. But now there is a subtle thing, is that you say, yes, but the rotation is not the rotation of the Earth. It has to be the rotation of the Earth at the considered points. Okay? And as the Earth is a sphere, you see that the projection of the rotation on the axis perpendicular on the vertical, the local vertical, changes, okay, with the latitude. And the geophysicists make an approximation. They said it is the beta plane approximation. It's just to say that they take the first order variation of omega versus the latitude. Okay, this is the first term in the Taylor expansion as a function of the latitude. So you say that this is the coefficient, but here I said beta c. I put a c because I don't want to mix up with my wave numbers. And so you write the 2 equations here. Okay, the du, dv, y is a function, omega is a function of y, the latitude, and you play with this equation. In particular, you can calculate the vorticity, and you end up with this equation here, d omega z dt minus 2 d omega y dy v equals 0. And you see the interest here, because you have the derivative of y versus y. So if you take y as a linear function, this will be a constant, and the constant will be beta. Okay. So now you plug, as before, the wave shape, and you end up with omega equal minus 2 beta c alpha divided by alpha squared plus beta squared. And now you see that there is, so here this thing will not change sign, and omega on alpha have opposite signs. Okay, we say beta c is positive. So that means that d omega over d alpha, in fact, has always the same size, and that means that the Rossby waves, these are these Rossby waves on the Earth, okay, that propagate always, because omega, the phase velocity, omega divided by alpha is negative, always propagate towards the west. Okay, so these are the Rossby waves. Okay, so you asked me if they were dispersive some minutes ago, Benjamin. Yes, you see they are, because the phase velocity is changing a lot, for instance, versus alpha. In fact, these waves they take the name of Rossby because Professor Rossby worked on these waves a lot. And this is a photo of him in front of an apparatus. We can do these waves in a very simple apparatus. So we take a cylindrical box, which is rather flat, here, like this one, with a very subtle thing, which is that the bottom is a cone. Okay, the bottom is like that, and it is a cylindrical wall all around. Okay, you put 20 centimeters of water there, and you try to search a solution because it's quite flat. du dz equals 0, dv dz equals 0, and here I will add something which is d over dy equals 0. That is the variation along this direction y, here, the radius, is neglected. Okay? So I have to say, I neglect the curvature of the apparatus. Okay? Imagine that the cylindrical tank is large enough so that you can neglect the d over dy. Okay? So you search a solution of the system, and you have to impose in the lab non-permeable bottom conditions. Okay? The flow cannot go through the bottom. And if you write that, it is v perpendicular to bottom is equal to 0. What is v perpendicular? It is equal to omega, the vertical velocity, cosine the angle theta here, plus v, blah, 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 at minus h, sine theta. And you end up that the velocity w, okay, which